Okay, so let's do number one. Draw a vertical line so that about 80% of it is to the left of that line. About 80%. Yep. Now I want you to change number 2 here, just so that I just want to make one a little different. So let's change that to 30%. So now draw a horizontal line so that 30% is above that line. About a third of the rectangle is above it. Which would mean 70% would be below it, right? And again, estimates. So this is 30%. This is 70%. This is 80%. This is 20%. Let's do this. Let's see if we can break. See if we can find the area or the percent of the total area of the original triangle of each region now. So is this going to be more or less than 30%? It's going to be less. So what would you say it is? It's 80% of 30%, right? So 80% of 30% is 24%. So that's 24% of the original rectangle. And this would be 6%. So for a total of still 30% in this horizontal row, right? This is going to be 80% of 70% and 20% of 70%.
Does it matter if you put 70
No. That was just kind of the way that we initially thought about it, but either way. Community property. So my point here is this, is that when you take a percentage of a percentage, I mean, that's going to be a smaller chunk of your original amount. Okay? So let's do this. Let's make a tree diagram for the situation above. Now, one thing about tree diagram is that you don't have to balance the branches equally. Okay? So like for example, if I had two reds and one green pen in a desk, I could take out a red, or a green, but you could also write this as I could take out a red or a green, and I could say there's a 2/3 probability of this and a 1/3 probability of that. So that's another way that we'll write our tree diagrams, with weights or probabilities next to them. So what's this? The chances that it's left? 80%. Chances that it's not left? 20%. Chances that it is left and above. Well, above is 30, so 80% of 30, or 30% of 80, right? Left and not above would be 70% of 80%. So it's the same thing, I'm just representing it a little differently. Well, that's 6 here, and this is 14. Okay? Any questions on that? Okay, let's look at another one. Now a little bit more verbal, a little wordier. So let's say that the probability, let's say I have a group of people, and the chances that I pick a junior out of that group is 25%. So not junior is its complement 70%, right? Okay, let's look at this. Let's look at the restriction that we're only talking about juniors. The chances that they would be in an activity is 60%. So then with that restriction, the probability that they're not in an activity is 40%.
It doesn't matter if we put the actual percent or do you prefer decimals?
I don't care. You know, the reason why I do it this way is because we're going to do arithmetic with them, so I just leave them in decimal form, so we do the arithmetic. Okay, with the restriction that you do not have a junior, the chances that they're in an activity is 45%. So would you say that these events are independent or dependent? Right, because this restriction affects the chances of them being in an activity, right? Okay, not a junior, chances that they're not in an activity, 55%. So, we have dependent events. So I want somebody to tell me the probability of A and B for dependent events. Given. A, right? Okay. So again, when they're dependent, you have to have that given probability, that conditional probability in it. So we kind of said that we have a dependent situation, so I'm going to write this out. We'll write maybe a couple of them out, not all of them. So this would be the probability of a junior times the probability of being in an activity. You can abbreviate however you want, given that they are a junior. So this again is 25%. This activity, given that they're a junior, 60%. So that is going to be 15% chance that you pick somebody that's a junior in an activity. So this one, probability that I pick a junior times the probability that they're not in an activity, given that they're a junior. So 0.25 times 0.40, and that's an overall percentage of 10%. Okay, you write out the formula for the next one and then calculate it. The number 3.
And then for now, we put down a little squiggle thing.
That's what I do. You know, just write squiggle here instead of the word not, whatever you want. So, hopefully you can do that. This one, if I multiplied it out without writing all of it out, I'm going to say that it's going to be 0.75, just like this, times 0.55. So again, just kind of, I want to take you through this just like we did in the last one here. Just kind of put it together. Chances that you pick somebody that's a junior is 25%. So chances that you don't pick a junior, 75. What's the chances that they are in an activity given that they're a junior? That would be 0.6, and then that product is this guy, 40%. Junior not or junior and not in an activity, that product. Okay, so hopefully 45, 55, same information is up here, but just kind of in a flow of how it's happening. You may have a question you want to ask about this. Okay, so then let's do this. Let's go ahead and look at our assignment here and maybe ask and answer a few questions off of your assignment, okay?
So is this one due tomorrow?
This is due tomorrow, so after I'm done, you guys get a chance to work, okay? Okay, so go ahead.
For number 27, it says like a person in the United States may be like 5 unrelated people, or what for the population. Like when you like, I don't know.
Okay, so let's look at 27, okay? Actually, let me look at 25 a little bit, and then I may jump to 27, okay? Because they're a little bit different, okay? So number 25, and then we'll do 27. So it says in a sample of 2016 U.S. adults, that's a number, that's not a year. Okay, 383 said Franklin Roosevelt was the best president since World War II. 2 U.S. adults are selected at random without replacement. Okay, find the probability that both say that he was the best. So we're looking to find out the chances that the first one says that the president was the best and the second one says that he's the best. Okay, when we do it without replacement, what does that mean about the probability of the next event? It changes. So this is a dependent situation. So really, this is what you're doing. And I would really like you to write down your work. I told you this, write down what you're trying to find, read it how you want, write your formula down, and then let's figure it out. Okay? So, out of the 2016, the chances that they said he's the best would be 383. Now, that's not the same the second pick. The second pick is going to be what? Right. Okay? Now, if you work this out, give me a decimal to 3 places. Zero, 3, 6. Okay. Now I would bet if you would have not done this without replacement, it would be approximately the same thing to like even the thousandth. But I want you to understand that this is really the right way of doing this one. Okay. What about part B, where they say that what's the chances that neither adult said he was the best? So then the first person says he is not the best, and then the second person says he is not the best. So I think you could figure that out. Okay? And I'm going to stop talking about that. I just want to make sure that you get the idea that that's what we're looking at to start with the problem there. Okay? Anybody have any other issues so far on that? Okay, so let's jump to 27 and let's answer 27 now. Okay? So let's understand the problem. It says the probability that a person in the United States has type B positive blood is 9%. I'm B positive. Five unrelated people in the United States are selected at random. So the reason why they're saying they're unrelated is that makes that the chances are going to be the same randomly for everybody. So like if we have related people, the chances of somebody having the same type of blood is going to be dependent on what mine is. So there's a dependent situation there. So we're really kind of saying that there's an independent probability. Okay? So you don't need to do any dependent probabilities here. Okay? So find the probability that all 5 have B positive blood. So I would say that we want to know that the first one is B positive and the second one is B positive. So let's just think about what we just got done doing. What's the probability that just one is B positive? 9%, right? What's the chances that you have B positive and B positive? Isn't that going to be 9% of 9% of the time that you're going to get 2 consecutive B positives? Okay. But we don't have 2, we have 5. So if we think about the 5 consecutive B positives, we're going to have 0.09 to the 5th. Okay? So that's not very likely, right? So my calculator says this. What in the world is this? 5.9 e negative 6. Right. E negative 6. So that's 5.9 times 10 to the negative 6th. So really, really small, right? So 1, 2, 3, 4, 5, 6 places. So essentially, there's no chance of that happening. Okay? Everybody with me on 27A? Let's do B. Find the probability that none have 5. None of the 5 have B positive. So what's the first one got to be? Not B positive and not B positive. And again, does this make sense that I'm not worried about the dependent part here? You know, we don't have to worry about that given stuff because we're saying that they're independent picks. Okay? And now here it's going to be not B positive times itself 5 times, so 0.91 to the 5th. Okay? Which is actually, that could happen. Okay, let's look at C. So C says find the probability that at least one has B positive. Well, that's crazy, because you could either have one have it, it could be either the first person, or the second person, or the third person, or the fourth person, or the 5th person, and nobody else, or the first 2 and not the last one. That's a mess, right? How in the world are we going to figure out all of those things added up? Find its complement. What's the complement of at least one person having B positive blood? What is the opposite of that? Nobody. So calculate that which we've actually calculated. No one has B positive blood out of the 5, and we know that when we just calculated that. Was it 64? 62, 4? So then the chances of 1, first or the second or the third, or 2 or 3 or 4 or all 5 having it would be the complement of that. So 0.376. So that one's a tough one because you got to think, you know, at least one. Opposite of that is nobody. Okay, and then the final thing, it says which of these events can be considered unusual? Is this unusual? Nope. What do we mark as a probability that's unusual? Less than 5%. So this one would be unusual. Okay. So use this time. Get to work. Here's the deal. We are going to review, and I'm going to hand this out to you. So if you've got partway through this assignment, you can kind of start on the review. You do submit it. When you're done submitting it, you'll see the answers, and then we'll test on Friday. So we'll have some time to hit and talk about things tomorrow.